Hello all, I welcome you all to the last lecture of this course EE614. We will spend a few minutes in summarizing what we have seen till now. We started off with a goal of trying to understand the thermal characteristics of various devices that we have previously seen. That begins with a PN junction diode, a bipolar junction transistor, as well as the most commonly used MOSFET. Right, so we have a gate oxide semiconductor, right? And we have seen about the terminal characteristics many times around, and we wanted to understand what lies beneath these device structures to give such nonlinear characteristics. So to understand this, we started off in trying to understand what an atom is, and we saw some very preliminary but then path-breaking experiments, starting from the Thomson's experiment on electron, as well as the Millikan's experiment on charge on the electron. By then, we started to go through the Drude's experiments, the Drude's model, wherein we saw that you can derive the Ohm's law if you assume that the electrons in the material act as kinetic atoms in a gas, and some of the peculiar conclusions from the Drude's model, which is the Hall coefficient, which turns out to be always negative if what Drude assumed was correct. We saw that that is not always true. Experimentally, there are some metals which show even positive Hall coefficients. So to understand that, you have to understand that the electrons do not lie in a random material, but then it's easier to see if we can assume some sort of a crystallinity. And crystallinity means that you have atoms which are periodic in space, and then we have what is called as lattices. Lattices are mathematical constructs, and we saw about various lattices that are possible. That is simple cube, body centered, face centered, and stuff. The most important for our for solid state devices was the face centered cube, because most semiconductors tend to form this. If you have a face centered cube with a 2-atom basis, we saw that you are most likely to get the valence band completely filled when you have temperatures close to zero. And we also saw about Crony-Penning model, where the simplest one-dimensional electron lattice can start to give you energy bands. And you see that if we can represent these things in the reciprocal space, then you can clearly distinguish between electrons with momentum smaller than the first Brillouin zone, and later on you can clearly see what happens if you have two free electron dispersions meet to give you an energy gap, right? And with this understanding, we came to understand about carrier densities in material, and then we know that there exists this equation which is called as the Fermi-Dirac integral, which gives you what is called as a density of states. So our previous treatment tells us that you cannot have infinite number of electrons, because electrons are fermions, and hence for a given energy you can have only two electrons, one of them having positive spin, another of them having negative spin. And it is this distribution which gives you that which tells you that you have what is called as a Fermi-Dirac distribution as given here. And you have the density of states which go square of electrons. We also derived this. So you have a density of states which go like this, and you have a Fermi-Dirac function which is like this. The overlap integral of this gives you the net number of electrons in the material. We also saw that you can use what is called as an effective density of states for electron and effective density of states for hole, and then we use these parameters to understand electron statistics in semiconductors. We saw different kind of semiconductors, the intrinsic one, the extrinsic one, in this particular region, and then their behavior at various temperatures. At low temperatures you have what is called as freeze out, and then at very high temperatures even an extrinsic semiconductor behaves like an intrinsic one, and so forth. And when you have such electrons in a material, then there are different kinds of transport characteristics. One is the pure drift transport. As we see here, the velocity is proportional to the applied electric field. And you have what is called as a diffusion transport, which, as we've seen here, is driven by gradient in the electron concentration, or gradient in the charge concentration. And then we derived this beautiful Einstein's equation, which relates diffusion coefficient D with the drift coefficient mu, and they are related just by this thermal energy, that is kT by Q. So we have this beautiful expression. So once we understand various carrier dynamics, we saw that there are few equations which determine the carrier transport in most semiconductors. We begin with these three current equations, which says that total current in any semiconductor device is summation of both electron and hole current here, right? And the electron and hole component independently constitutes a drift current as well as a diffusion component. And any change in carrier density is determined by this continuity equation, which is defined as change in carrier density per any time d is given by the generation term minus recombination and the difference between the incoming and the outgoing current, as seen in this particular diagram. We saw some very important experiments, Stevenson's-Keynes experiment here. We take a semiconductor, shine light, and then see how the minority carriers decay over time. And we take a semiconductor, apply a bias, and then shine light, so you have a Gaussian profile, and how the Gaussian profile changes over time. This is called as a Schottky experiment, right? So we use these things in many places throughout the course, and we use this even to understand PN junction diode, which is what we saw next. Here comes my beautiful drawing from here on. So you have a PN junction, a P-type semiconductor, an N-type semiconductor meeting at equilibrium, in the sense that there is no steady state current flow through this particular device. Even in the situation, you will have some potential at the interface, and that potential is proportional to the doping density, and the width of the depletion width depends on the root of the potential that is applied. So this is something which we will see repeatedly during our course. And the total current and any applied bias is summation of the electron current and the hole current, as seen here, and this is how they distribute. And the current is predominantly carried by the diffusion part in most cases, because the carrier densities, the minority carriers on either side is much smaller than the majority carrier concentration, and hence the drift component is significantly less when compared to the diffusion current, and hence the total current is only the diffusion component. And we derive the equation, which is called as the Shockley equation, or the ideal diode equation, and we found the expression for the reverse saturation current to depend on the inversely on the doping density and on the semiconductor intrinsic carrier density. We saw various non-ideal effects, generation and recombination in reverse bias, series resistances in the forward bias, and other conditions called like high injection and such. We also saw about junction breakdown, thermal instability, tunneling, avalanche breakdown, under what conditions which breakdown will dominate, and this tells us or helps us to understand why our diode has this kind of a behavior, right, from where it breaks down. So this is the typical breakdown characteristics, and how it will change depending upon the material of the diode and what temperature we are operating, and so on and so forth, right? Finally, we saw some interesting aspects as to what happens if you switch a diode from the reverse to forward and forward to reverse. We show that when you have a diode which is operating at forward bias and then quickly turn it to reverse bias, it will not be able to turn off the current very quickly, and hence you will have the current to display this kind of a dynamics. So this is IF. If you switch the voltage at time t equal to 0, it will sustain a constant minus IR equal to IF for some time t1, and then exponentially die down t2. These are the two time scales that we saw, and then you have this expression for these two. And now This is the reason why whenever you have a bulk charge transport characteristics, you will have what is called as the charge storage time, and hence it will not allow you to switch so fast. That's why BJT is not a great device in comparison to a MOSFET, which is having a sheet charge density. We also saw some interesting aspects of PIN junction diode, where the depletion capacitance does not depend a lot on the applied bias, but then it depends strongly on the intrinsic layer that you have. So it will have almost a constant depletion capacitance, and it also has very interesting RF characteristics, as we saw during our detailed discussions on PIN junction. It is used as a resistance in a pure resistance in RF domain and such. We also saw interesting characteristics of capacitance in forward bias. So you have in reverse bias, you have what is called the depletion capacitance, which dominates. When you have a forward bias, then you have a capacitance due to the minority carrier concentration not responding as fast as we want, and then hence giving you a capacitance which is called as a diffusion capacitance. We derived an expression for diffusion capacitance, and it is this diffusion capacitance which dominates in forward bias. So you have an effective model of a diode in reverse bias and a model of a diode in forward bias in this particular format. Finally, after the diode got over, we started to discuss about metal semiconductor junctions, and then we saw that the barrier for electron transport from a metal to a semiconductor or semiconductor to a metal is purely a material parameter, which is called as a Schottky barrier, which depends upon the metal and the semi-metal work function semiconductor electron affinity. But whenever we come up with a simple expression as we have here, we always have an exception. So when you have very high field at the interface, you have what is called as an image force lowering, as we saw here. And when you have very high doping density, then you will have a barrier which is so thin, so electrons can basically tunnel through. So the current transport characteristics through a metal semiconductor interface typically have several contributions. One is called as a thermionic emission, another one is called as field emission. Field emission or tunneling depends or strongly dominates the interface transport at low temperatures and high doping density. At high temperatures, you have thermionic emission, and in any condition in between, you have summation of both thermionic emission and field emission. This is something that we discussed when we talked about metal semiconductor interface. Next, we talked about BJT. BJT is nothing but a PN junction diode connected back to back. But then we saw that the main purpose of having such a structure is that if we are able to control the electron injection into a depletion width, then you can basically control, you can basically have a constant current source whose value you can change, right? Because you typically wanted to have somewhere here, you want to work somewhere here, but then it is this current, that is the constant current characteristics, which you would like to change by changing the emitter injection. And so this is basically what was required, and that's when the BJT actually started to be used, right? And this is reverse bias junction. This is basically your base collector junction, and then you change the emitter injection to jump from one current level to other. So this is an ideal current source because the current value do not change with any change in the bias that you have applied until you reach a particular point. That's the difference. So there are several currents in a BJT. We saw that you have an emitter injection current, you have recombination of the emitter, you have a whole injection into emitter, and so on and so forth. We calculated these values specifically, and then we calculated what is called as a base transport factor. You have emitter efficiency, and then we saw its dependence on what is called as the Gummel number, which is an integrated doping density in the base. And we saw that there are several combinations, several configurations that you can have a BJT in. The common emitter is the most common one, and the gain, the common emitter gain HFE, depends strongly on the collector current IC, and then it behaves almost linearly till some IC, and then starts dipping down because of you have high injection in the base collector junction. This is what is called as Webster's effect. In addition, we also saw that the transconductance GM also depends linearly with IC. This is important for applications in amplifiers and such. As we saw previously, there are two configurations. One is called as the common base output, common base configuration, where the input is from the emitter side and the output is the collector side. The gain is almost equal to 1. So you have what is called as a constant current characteristics, which is useful for a current source kind of applications. You have a second kind of device which is called as a common emitter case, where you have a strong change in the collector current with the collector emitter characteristics. You have three regions of operation. Basically, you have a cutoff region, you have a linear region, and you have a saturation region. And these regions are determined by how do you bias individual junctions. And we went into details about what determines the slope of the current here, and then these slopes can be shown that they will meet at one point which is called as an early voltage. And the early voltage, higher the early voltage, the flatter these curves are, and the flatter these curves are, the better current sources they are. And it also, the early voltage also depends upon what is called as the Gummel number, as which is shown here, right? Finally, we saw about non-ideal effects, particularly emitter band gap narrowing, in the sense that you typically want a very high emitter injection, so that you typically dope the emitter strongly. But then when you dope the emitter strongly, you have other effects, right? Because of band gap narrowing and stuff. You have what is called as a Kirk effect, where the depletion width in the base collector junction is moved towards the collector contact junction, as it is shown here. And you have what is called as current crowding, because of the fact that our base contacts are not in line with the injection path, so it has to bend, and you will have all sorts of effects because of that. We saw some very different capacitance configurations in a BJT, or different number of capacitances, the depletion and diffusion. But then you also have what is called as a space charge capacitance. This once again comes up because of the fact that you have minority charge carriers in the bulk, and these minority charge carriers do not respond as quickly as we want, and hence it has a capacitance associated with that dynamics, which seriously limits the high frequency operation of a BJT. After the BJT, we came to look at metal oxide semiconductor junctions. We saw that the capacitance acts as if there are two, the total capacitance of the device acts as if there are two capacitances in series, the gate oxide capacitance and the depletion capacitance. And the depletion capacitance depends upon the bias that we apply, and hence you have total capacitance which behaves something like this. When the bias is larger than a particular value, you deplete the channel. When we mean that, if you first deplete the channel and then you invert it. When we invert it, we mean to say that you have a carrier density equal to the majority carrier density of, you have the okay, let me rephrase. We have a minority carrier at the interface equal to the majority carrier concentration because of the field that you have applied. So it is called as a channel inversion. And you can typically have two kinds of MOSFET with this inversion. You can have a N-type MOSFET or a P-type MOSFET. You can have an inversion to begin with and then deplete it to turn it off, or the other way around. So there are 4 different configurations in which a MOSFET exists. And then we saw several output characteristics and such. We spent much little time on MOSFET in comparison to the BJT and PN junction diodes, because there are dedicated courses on MOSFET, whereas this is supposedly the course to be dedicated on diodes and BJTs. So with this brief summary, I stop my lecture now to thank you for the time that you have given me. I have learned myself a lot when I'm teaching this course, and I hope that there is something that I have taught you in addition to what you had previously known before you came into this course. So I would like to thank you for your attention as well as for the patience, because this is the first time I'm teaching the course and this is the first time we did it online. So there might have been some hiccups, as I said before. So I hope you had enough patience to sail through this course. I wish you all the very best for the NSEM. And as always, any questions, please do mail me. Thank you.